Hey class, Adam Ward here. So we have planned our slug injections. Now let's talk about how we actually pull this off in the field. And just a note here, I'm taking images from a blog post by Adam Listowski and others from several years ago to help show us how this is going to look while we're out in the field. Okay, so step one is to select our study reach and our mixing lengths. And so what we're going to want to do is decide where is it that we want to study. We need to establish a location that will be upstream of our solute tracer study and will remain upstream for the duration. We'll call that our background site. We'll pick a location to inject with some mixing length. And immediately below that, we'll put one of our loggers that I've written in purple. Now, I acknowledge here I'm writing the word logger thinking that you're going to deploy something that's going to collect high-frequency samples, like a fluid conductivity logger or a field fluorometer. If that's not the case, or if you're using a tracer that doesn't have a field deployable logger, or you are not in possession of one and you're going to collect grab samples, those locations that say logger, those would be the places where you're going to actually collect bottles of water. So you're going to very rapidly collect samples for analysis later. Things that we'll want to think about then are study reach. Well, that's going to be the location in between the two loggers. Everything upstream of that first logger is just the business that's required to do the test. So what we're actually studying is in between these two loggers. Things that we're going to want to measure in the field. We're going to want to know the width of our stream, either a representative cross-sectional width or a distribution of widths along it, the average depth or a couple of cross-sectional surveys of our study reach, and of course the length of stream between the two loggers. If you've got the opportunity to measure hydraulic conductivity or grab a soil sample for subsequent analysis, that's a helpful thing to do. And my strong suggestion is that you at least conduct some survey, either the major geomorphology or some notes. And so, for example, if I don't have time to do a complete topographic survey, I'd still like to walk along the stream reach, ideally when I have a tape measure stretched so I can locate where these things are. And I'll identify major features like a debris jam, pools, riffles, a bedrock outcrop, just to help make sure our field notes are complete to describe the reach that we're studying. And as you can see in panels A and B on the left, photographs absolutely help you when you're trying to analyze this data later to remember what the system looked like at the date and time when you did your study. All right, so with this strategy in hand, if you are going to use field deployable loggers, you want to make sure that your wristwatch or your telephone that you're using for time with you, your computer and your loggers are all collecting data and the same temporal reference. In other words, we don't want things offset in time because of differences between a watch that might be set different. If you are using loggers, my strong suggestion is to put some bright flagging or some tape on them. In our group, we also label them with a unique ID so that we are sure that we know which logger is at which location, and of course that we can find it back at the conclusion of our study. If we're using loggers, we try to go to sort of the highest temporal frequency. We can always downsample our data. We can never upsample it. We can't create data, we can only destroy it. Sort of the Newton's less famous law, I suppose. The other note, if you're using a logger or a probe, many of these are going to be temperature dependent. And so in order to get the best possible data, we'd like to get those loggers or those probes into the water early so that they have time for the logger, for the optics or the circuitry that's going to be used to equilibrate in temperature with the stream water. So get these things deployed and get them in the stream so they have time to come up to a steady temperature. With everything deployed, this is time where we want to start collecting our background or our pre-tracer observations. This can happen not only where you have the two loggers, but you should also get a background sample at the very upstream end, where a few slides ago we labeled it with the word background in orange. So we want to have those so that we're sure we understand what the concentrations are in our system prior to our tracer being deployed. All right, now it's time for our injection. So we're going to prepare the injectate. Ideally, what we'll be able to do is use either a small bucket, like a 5-gallon bucket shown here, or a trash can. We'll fill it approximately halfway with water from the stream. We'll add our tracer. And if we've had that tracer in a Ziploc bag, if we've had it in a vial or a small bottle, we want to rinse that not in the stream, but in the bucket. So your rinsing should be into the bucket. And we're doing that because it's really critical that all of the tracer mass that we prepared in the lab makes it into the bucket and ultimately into the stream. We like to take a short length of PVC pipe with us into the field when we use that to stir the bucket or stir the trash can to make sure that it is well mixed within the trash can and that our tracer is fully dissolved. Here you can see an orange bucket being used. That's not an accident. When you're using a salt tracer like sodium chloride, where it's a white granular substance, doing it in a white bucket can be difficult because you can't see the grains. So a colored bucket helps us know that we can visually look down through the water column and we can see our tracer is dissolved in the bucket. Now, again, I'm going to emphasize this point several times. All of our analysis is predicated on the idea that we know how much tracer mass we put in. If you don't rinse the bag or the vial, if you splash tracer out of the bucket while you're mixing, you don't have 100% anymore. And that's an error that will propagate through the rest of your analyses. So we want to stir, but not so vigorously that we're going to mix, that we're going to splash any water and tracer out of the bucket. All right, with our tracer mass ready to go, it's time to actually release our tracer. Critically, we want to note what time we're actually going to do our release. What I will typically do is look at my watch, pick a time that is about 30 seconds into the future, so I can write that down in my field book, set my field book down, and then I watch for that time to arrive so I can do the injection at the exact time. What's actually happening here? We want to rapidly empty the bucket into the stream at the center line. Now we're picking the center line because that will give us the most rapid mixing across the stream as opposed to an injection on one bank. But that's not the end. Again, we're going to take care not to splash our tracer onto rocks, onto the banks, onto vegetation, again because we want that mass in the water. After we've dumped the bucket out, just to ensure we have 100% of our mass getting in, we want to very quickly take the bucket that we've used in photo 2 and the mixing rod in photo 3 and give those a quick rinse in the stream. So we don't want to do that 5 minutes later because any mass that would be stuck is going to now be delayed or offset from the rest of the pulse. So as quickly as possible, we'd like to make those rinses and get all of that tracer mass into the stream. Okay, so what's going to happen? This is what the time series might look like at one of your loggers. We have it deployed prior to our injection for plenty of time to characterize the background in the stream. So any variability for our logger to come to a steady state, we've done this. Now, as the pulse arrives, those concentrations or fluid conductivities in the case of the salt tracer we've been looking at go up to their characteristic peak, and then they start to slowly relax back down to background. We'd like to leave our monitoring to continue until we've returned to background conditions. This is particularly important to achieve. We can't go back in time. We would rather collect too many samples in the field, collect too much data on a logger, and truncate that later as opposed to missing the tailing behavior, which becomes very important for some of our subsequent analyses. So just to drive home that point, we cannot go back in time. We would rather deploy these loggers or stand out in the field collecting samples for too long than to truncate our experiments and come home too quickly. Finally, that the background location upstream of our injection point should be sampled regularly through this period as well. The reason we do that is to make sure that we have a constant concentration entering our study reach. And we know that that's independent of anything due to our tracer. So that upstream-most background sampling site is critically important to keep track of through our study. Okay. So we want to be able to check that the starting and ending points are not at different baselines, which would indicate some shift in the system. All right, folks, so that's what a field injection looks like for a pulse or a slug. In short, we make our background measurements, we prepare ourselves to collect our samples, either manually grabbing them or by deploying our loggers. We make sure our tracer is fully dissolved with some stream water. We rapidly release it into the stream, taking care to rinse the bucket, rinse the mixing rod, ensure that mass is not lost by having it land on a rock or on vegetation. And we continue that monitoring at the background site as well as our logger sites for as long as we need to ensure that we've returned to background conditions. All right, thanks everyone. See you in the next video.